high northern latitudes of Mars. Okay, something else fun that we're doing is observing new gully activity on Mars. So these are sand dunes here, and what's happening is we get what we've called gullies on Mars. It's actually a composite landform with an alcove, channel, and depositional apron. And this is active. Every year, around late winter, we see new activity in the alcoves, changes or enlarges the channels, deposits new lobes of dark sand. And there's quite a bit of this activity and a fairly large scale. And we've realized that the reason why this wasn't detected previously wasn't resolution, it was signal to noise, because it's dark sand, basaltic sand. The active ones are at high latitudes where the illumination is poor, especially when these are active, and the atmospheric conditions are often poor. So we're trying to get a complete inventory of these. These things are active, to our surprise, in the late winter. So that's the time of year when there's the most CO2 frost on the ground, and there's some connection there that we're still puzzling out. There's also gully activity not associated with dunes, just with the slopes of craters. This is one example. There's 5 different images, a little cutout blown up here. You probably can't see it, but there's boulders here, but they're different boulders in different places. So that's some of the activity here is moving meter, 2 meter scale boulders around. Another fun observation are polar avalanches. This is CO2 frost and dust avalanching down this very steep scarp, about a 60-degree scarp here on the edge of the North Polar Layer deposits. And this is airborne dust associated with this avalanche that's just happened. The dust is still settling, basically. We get stereo data acquisition with HiRISE and this whole family of cameras that I've described, but pretty much always from 2 separate images, separated in time, pointing either the spacecraft or on Galileo, a scan platform, to get 2 images at 2 different viewing angles. This can then be used to produce high-resolution topographic maps, digital elevation models. And we can do fun things with this. Many people get the impression that Mars is Kansas. It's very flat. Every landing site, it's this flat terrain. Well, Mars is topographically very rugged. We just don't land in those places. And this is from inside a piece of Valles Marineris. If you were sitting on top of one of these hills looking out, this is, without vertical exaggeration, what some of this topography looks like. The colors are enhanced. Here's yet another digital elevation model of a central peak of a crater. Okay, so let me move on to LROC. And LROC has been mapping the moon for about a year now, almost a year in its low orbit, in fact. And it has already outdone MRO by a factor of several in data volume return. But one of the things that's been the most fun with this camera is finding all of our own debris on the surface. That from our, back in the 60s and 70s, we actually used to land things on the moon. And that stuff is still there, and unlike Mars, where things get altered from active processes, they're pretty much pristine on the moon. Nothing much happens there. So I just picked out a few examples. This is Surveyor 3, and so that's the lander right there. Here's Luna 20. The Soviet Union sent big landers, so they're fun to find. And in many cases, we didn't really have a good idea where they were on the moon in relation to surface features. And this has been quite interesting. Some of these return samples. This was the first unmanned sample return we did in 1972. But in some cases, we had no real understanding of the local geologic context for interpreting those samples. We're getting that now. This one is Luna 24, and this one in particular, the sample is better understood when realized that it is on the flank of a fairly fresh crater. Here's the Lunokhod 2 rover, the first rover sent to another planetary body. We've also made some impact craters on the moon. This is the Apollo 13 upper stage, which followed the LEM in its drama-filled journey to the moon and back, but it crashed into the moon and made this crater here. Ranger 9 was intended to crash into the moon, an image on the way down. We're also finding new impact craters that are created naturally on the moon. This is comparing Apollo Pan image from almost 40 years ago to the LROC images, and you can see most of these are duplicated, but there's a nice bright fresh crater here that wasn't present in the previous image, about 10 meters diameter. Okay, so what's the future of high-resolution remote sensing of extraterrestrial planetary surfaces? Why not send HiRISE-like cameras all over the solar system? That would be wonderful. But the mass is still relatively high for this type of thing. Light weighting is expensive and risky. As we see from JWST, we can't afford to do that for every mission to every planet. Power is an issue. The average is about 60 watts. It's still pretty high. CMOS detectors are going to help here significantly for lower power. But probably the biggest limitation really is the mass and power needed to send substantial amounts of data back to Earth. The need varies with range to Earth, of course. The use of more Ka band helps by a factor of a few, although often you need the X band as well, so it's more stuff to have to fly. NASA is not maintaining their 70-meter antennas, unfortunately. The hope for the distant future, at least, is optical communication. And NASA has plans for optical communication, or at least they have view graphs, and here's one of them. A recent presentation from the Space Communications and Navigation Office, which includes the DSN, to the National Research Council, showing optical comm from the Moon, Mars, and Saturn. So why optical comm? You can get order of magnitude sort of increases compared to radio frequencies to get more high-resolution imaging and extensive coverage and high data rate spectroscopy and so forth as well. Lower size, weight, and power burden on the spacecraft, which is, of course, the limiting factors. But there are technology challenges. It's very sensitive to the weather. And what's being considered is to put receivers in Earth orbit for optical comm, which leads to a number of challenges. It also has very tight pointing and stability requirements. So this is not a mature technology yet. There is a demonstration of optical comm planned for the LADEE mission. That's the Lunar Atmosphere. It's a very small mission run by Ames, which doesn't have any high data rate instruments, so it won't benefit scientifically directly from optical comm, but it would be a first demonstration of it. That's launched for that is coming up sometime in the next 5 years or so, I believe. Here's also from the same presentation, the next step where we really benefit directly from optical comm is probably going to be Mars. There's, of course, great interest in Mars for potential future sample return and future human exploration. So from this view graph, and that's all I know about it, they're talking about a 30-centimeter deep space terminal. They supposedly have a high fidelity cost estimates, and they're talking about 30 megabits per second from Mars when it's at its average distance. Modest mass and power requirements, maybe 2018 launch. And in particular, there's discussion in other view graphs about these robotic precursor missions. That's in Obama's new space plan for NASA, if that ever becomes reality. But one of these robotic precursors is an orbiter to Mars for a variety of purposes, including optical comm with very high resolution imaging, with view graphs talk about getting down to 10 to 20 centimeters, significantly better than HiRISE. Even if it were just a reflight of HiRISE with optical comm, you could have at least 10 times as much coverage of Mars at that scale. So this would be wonderful, but it's a ways off in the future. So my conclusion here is that the cameras are getting better, but NASA needs to improve the deep space communication for significant progress in high-resolution imaging beyond the moon. Optical comm might be the way for the long-term future, but it takes a while for that to get in place. And then if you're talking about the outer solar system, there's a 20-year planning lag here from when you build a mission and when you finish getting all the data back. So hopefully we'll have some other solution in the short term, such as arraying 34-meter stations. I'll stop there. Thank you.